a lot of voice resources, so I need this
Recording.
I'm pleased to see you all here, and I'm very pleased to say that today we have Professor Ziggy Cohen here from the University of Alabama Geography Department. And before I introduce him all, I want to thank the. Oh, we're not recording.
Yes. Wait, who?
Are you recording or is
No.
Stephen recording?
Oh, you.
Everything is recorded.
All right, thank you.
So I'm pleased to introduce Ziggy Cohen from the Geography Department at the University of Alabama. And before I introduce him further, I want to thank the Geography Department here at UF for allowing us to bring him here, and also the UF Water Institute, who is co-hosting this event. So thank you all for helping with that. Ziggy Cohen joined the Geography Department at the University of Alabama in 2012. Before that, he got his PhD in environmental sciences at the University of Newcastle in Australia. He then did a postdoc at the University of Colorado Boulder. And that he ended that in 2012. So a lot of things have happened since then, and I'm going to let him introduce himself a bit more himself. However, in his own words, his research focuses on computational modeling and geospatial analysis across multiple environmental science themes, including geomorphology, hydrology, natural disasters, and human-environmental interactions. And he's going to give us a taste of that today when he's going to speak about riverine research across scales, from flood forecasting to global scale sediment modeling. So please join me in welcoming Dr. Ziggy Cohen.
I hope it's good that my sound come across well with this thing. Well, thank you, Joanna. And as I'm sure many of you know, I've known Joanna and David for, I don't know, when did you join UA? At 16 or something? So for many years, and it was a great loss for us and a great gain for you guys when they moved here from UA. So I want to thank the Geography Department and the UF Water Institute for a very warm welcome. I actually feel like I came here for a job interview. It's like people are meeting with me and talking with me, and lunch with grad students. So I haven't had that for a while. I'm going to make the mistake I always make with these presentations. Just take this, which is to try to cover too much ground in a very short amount of time. And that's because, as you see in these pictures, these are some, not all, but many of the, especially grad students and undergrads and postdocs that works on all of these projects. And I found it really hard not to include their work when I present in these kind of talks. Maybe you can recognize one of the person in this, in a couple of these. So I have another connection to the UF Geography Department, which is Anushka here, was my former master student, and then she moved here as a PhD, and I heard she's doing great. So I'll get started. I'll talk about her research a little bit if I have time. So as the title suggests, I've done work at focusing on rivers from quite a few different angles. One of them, for many years, since I was a postdoc, I worked on global scale sediment modeling. I'll talk about it in the second half or the last third of my presentation. And I've also worked a lot over the years, and especially in the last couple of years, on flooding, especially riverine flooding. And that work has accelerated significantly in, I would say, the last 2 years, because as you see, my second title here is Deputy Director of the Cooperative Institute for Research to Operation in Hydrology, what we call CAIRO. So I want to tell you just too good to be true. Maybe I clicked on turn it off at some point. No, it should be on. Here
Is it working now?
All right, so CAIRO is a cooperative institute, which is an agreement between a federal entity and well, they're usually an academic entity. In this case, the federal entity is NOAA, and specifically the National Weather Service, and the University of Alabama is the lead of a very large consortium of 27 members of partners. I'm going to show you a map of those in a minute. I'm not going to go too deep into it, but I'm sure many of you are not too aware, or maybe just very vaguely aware, of the National Water Center that was established about 10 years ago by NOAA on the University of Alabama campus. The goal or the main emphasis of the National Water Center was to centralize research and operation in hydrology within the National Weather Service. And it now, or in the last, 5-6 years, it's been sitting under what's called the Office of Water Predictions within the National Weather Service, which is within NOAA. So the National Water Center is an actual building and an entity that sits on the University of Alabama campus. One thing I would say about it, we do run a summer institute every year at the National Water Center. And those of you who are students in the room who are interested in water, especially extreme events, I would highly recommend that you look into it. It's run by Kouassi and the University of Alabama and the National Water Center. Anyway, going back to Cairo. Cairo is meant to serve as the research arm of the National Water Center. So through appropriation by Congress, we get funding to support research, education, outreach, community building, and workforce development for NOAA. So it's a very good collaboration between us. And again, there's a huge consortium. The consortium is led, as I said, by the University of Alabama. And this has been going on for just under 2 years now. Funding a lot of, I think, very exciting research in a way that can advance hydrological forecasting and operation in the US. Let me skip that. I already spent quite a bit of time. So as I said, we are now focused a lot on the operational aspect of the National Water Center, which is trying to develop the next generation of hydrological forecasting, particularly at this point in time or in the last 10 or so years, mainly focused on flooding. So high extremes events, but not exclusively on flooding. Also, there's interest in droughts, there's interest in water quality and other hydrological issues. But what I'm going to talk about now is the research that I've been working on as part of this in terms of flooding. This work has started actually quite a while ago, but as I said, was accelerated dramatically in recent years. So here's our big motivation, or at least my group's big motivation. We have, when it comes to predicting floods, obviously you can use a hydrological model. That's how it usually works. You have a hydrological model that then predict the near or even further future in terms of how much water you're going to get in the rivers or maybe even runoff. So in terms of pluvial flooding. But that's great. That's very important. Predicting how much water you're going to have in the river. That is a really important step. However, the second step is how to map the actual flooding extent. That's a way to translate the hydrological predictions into impact and damage and how to make people aware and warn and evacuate and rescue and so on. So we want to translate the hydrological predictions of stream flow into flood inundation mapping. There are several ways to do that. One is use another model, which is hydraulic model that can simulate the fluid dynamics where the water moves, right? And through that, if you have the topography, the land cover, the boundary conditions, then you can predict where the water is going to go and how to predict their extent, the flood inundation. These are relatively expensive in terms of computational cost, data cost, calibration, and so on. So they tend to be quite problematic if you want to operationalize them over a country the size of the US at very high resolution, which is what we need to do in order to do it properly. So a more simple solution is to use just the terrain. So terrain-based approach, which is a lot of what I'm going to talk about today, which is the terrain tells us more or less where the water is going to go, right? So you can simplify that hydrodynamics into simple what we call a bathtub approach, where you can flood the domain based on the surrounding elevation. And finally, we can use remote sensing. I'm sure some of you have used remote sensing or learned or took courses in remote sensing. We can use satellite or aerial or even drones to map floods. Obviously, it doesn't tell you what the future is going to be like, but it is a useful data to have, especially in real time or historical perspective. So all of these have their advantages and disadvantages. And the way, or what the National Weather Service have opted to, or the Office of Water Prediction opted to, is to use what's called the height above nearest drainage approach. This is one of those terrain approach where you basically normalize the DEM, the digital elevation model, based on your nearest drainage. So instead of the height above sea level, the height of the pixel will be above its nearest drainage. And through that, using some concept called synthetic gradient curve, you can actually estimate the flood extent in the surrounding area of each ridge in the country, if you know what is the hydrological prediction. So how much water, basically the whole system, what it does, it takes the predictions from the national water model, a hydrological model. So we know how much stream flow we have and translate that into water height using these gradient curves, and then can spread that water in the surrounding land using this height above nearest drainage. Here's another UF connection. So the architect, I would say, or the person that developed a lot of this technology at the National Water Center is a former UF PhD student, Fernando, who was at the engineering College of Engineering. He still works on this. He lives in Gainesville, and he told me he might come today, but I guess he couldn't make it. So I made sure I had his name here. So, you know, he's part of a big team, but he was definitely extremely important in this development. So you can be proud of that. So, okay, this is the background of how they do operational flood inundation mapping at the whole the whole national scale, using this height above nearest drainage. Again, the reason why this is used is because it's extremely efficient computationally. You don't need very fancy equations, right? Fluid dynamic equation. All you need basically is a DEM, the gradient curves are static, and so on. However, like everything, there are major limitations to this approach because of its simplicity. And we have decided to try to address some of these limitations in my group to do some of the research. First of all, we wanted to know, think about it for a minute. Okay, you develop a model, doesn't matter, it's a complicated model, a simple model of flood inundation mapping. How do you know if it's actually working properly? And as scientists, we obviously have our evaluation techniques and so on, but which is important and very crucial to our work. In many ways, it's even more crucial when you try to do operational hydrology, because if you don't gain the trust of your end users, which is the forecasters or the public, then you basically have wasted your time. Because if people don't use your product, it's basically useless in the operational environment. So the way people have been evaluating a lot of these flood inundation mapping techniques is to compare them to other models, basically, or some ground-proof high water marks or so on. So we propose to develop a large repository of flood inundation mapping using remote sensing. And I'm going to talk more about that. It's something that I invested a lot of time in recently. So that's one goal that we have. Another one is to and I'm going to talk about each one of these points a little bit more, is to develop a better estimation of channel roughness. As I'll explain, this is a very critical parameter in this methodology. In the same way, thinking about the channel shape, better estimation of the channel shape. How do we actually estimate when flood begins? Think about it. I asked you to forecast a river, right? How much water that river is going to have. Okay, let's say you do a really good job at that, but still you don't know when or at what level the water actually spill over the banks and become a flood. It's not intuitive unless you have very good data, which we don't for the entire country. So we are working actively to try to come up with better estimation of bankful discharge. This is the point where you could have another drop of water and it spills over and become a flood. And finally, we want to start comparing all of these or many of these what we call FIM, flood inundation mapping solution to figure out which one works better at what situation, because this hand-based, this simple terrain-based approach generally works pretty well in like large floodplains, or if you have a really large flood and so on. They don't work at all in urban settings, for example, where you need very small scale, very nuanced understanding. So we're trying to find perhaps a better or optimized solution for these things. So I decided because I knew there was going to be a lot of students, and I know a lot of students here are not hydrologists and may not ever took a course in hydrology. I'm very quickly going to talk about the Manning's equation. So we have something in hydrology that's been around for many years, which is the continuity equation, which basically says that you can predict the discharge in a river as a function of the velocity, how fast the water are going within the channel, and the cross-sectional area. That's basically the area of the cross-section of the channel at a specific location. It makes sense intuitively, obviously very simple. If you know what is let's say the footprint of the water, and you know how fast it's going, you can predict the volume of it. Right? It's very simple conceptually concept to understand. And then we have the Manning's equation that's also been around for many years, to be exact, since 1795. And people are still using it all the time. And that tells us that we can predict velocity as a function of let's say this, I think, of the river slope, the hydraulic radius, which is this kind of it's a combination of similar to the cross-sectional area, not the same, some constant, and then the famous Manning's roughness coefficient. That's gives you the resistance of the channel boulders and whatever to the flow, right? The more resistant you have, the less velocity you're gonna have, right? So this Manning's has been a pain in the roughness for many years because there's really no good way to fully develop and calibrate it. So it's kind of been a catch-all, and it's extremely detrimental to predicting velocity. So we can combine the continuity equation and the Manning's equation to come up with an estimation of discharge based on the velocity, so the hydraulic radius, and then the Manning's equation. So why am I telling you all of this? Because this Manning, as I said, this Manning's is a really fundamental parameters in hydrology, and the way it's been estimated, or the state of the practice of estimating Manning's is either to calibrate it or to use these kind of lookup table. So you say, all right, I know you can't read it. So if I'm flowing on a concrete bottom with sides of the rest stone in mortar, then my minimum value will be 0.015. Anyway, you have a lookup table to find what is the Manning's value that you should use given the specific condition of your channel or river or creek or whatever it is that you have. Now, this is obviously not ideal. So we are trying to come up with a better way to do it. And we are now able to do it because we have the data that people before us did not have. And specifically, we have this data set called HydroSWAT, which basically someone that we should all thank very much took the effort of taking hundreds of thousands of ADCP observation by USGS technicians and compiled them into one data set. So the USGS technician, USGS is in charge of most of the gauge sites, river gauging sites in the US. They go and they take ADCP, acoustic Doppler array, river profiling, And they measure all the conditions, what is the velocity, what is the discharge, what is the width, what is the depth, and so on. And someone finally decided to compile all of this into one data set. So now we have a big data set and we can back calculate Manning's N out of this because we have Q, we have all of these other factors, so we can extract Manning's N. So this is a project that actually came out of the Summer Institute that I mentioned earlier. So this is a group of 3 students that worked on it on the summer, 2 summers ago. And we have a paper under review at the moment, hopefully it gets published. And they calculated Manning's N and they demonstrated that we can use machine learning to predict it. And they also demonstrated something new that's not, well, it's not new, but it's the first time it's been demonstrated at that scale, which is that Manning's N is actually not a static parameter. It actually changes as a function of how much water you have in the stream, which makes sense because if you have a lot of water, then the roughness at the bottom doesn't make as much effect on the flow as if you have very shallow flow. So that makes things actually even more complicated in terms of how to represent it. But that's one effort that we are going to continue on in my lab. The second one is we wanted to better represent the channel geometry, how the channel actually looks. I think people who don't come from this world of hydrology, myself included, actually, the first time that I get involved with this, I was surprised how little we know about the actual shapes of our river. We think it's pretty trivial things. We have rivers everywhere. We can see them. They're not unseen, right? But we actually have no way or no good way to represent their true shape or their true dimension for the entire country. And in this case, for the National Water Model and the National Water Center, they use over 2 million river reaches. So this is 14 million miles of rivers. So we just don't know, right? So the state of the practice has been for many years and still is to use power law equation to estimate river width and river depth as a function of discharge over drainage area. So these are called hydraulic geometry equations, and they've been used, they've been regionalized, so they become better, but they're still underperforming. They're not super good because it's just a power law equation. It's very simplistic. We have decided to use machine learning to try to see if we can predict it better. And this is a work of a couple of people, but mainly led by my PhD student, Riverine, and she have compared different types of machine learning and multi-regression modeling, and she found the optimal model that we can use, and we can now produce these kind of maps, which is river width and river depth for the entire CONUS at this scale, and the models are performing quite well. So it seems like we still need to test this, that we can improve the way we represent the channels in the country, and as a result, do a better job at predicting extreme hydrology and floods. That last bit we still need to do. One of my students, Riley, she's actually looking at, okay, from Riverene's work, we can figure out what is the average and bankful width and depth of the channel. What Riley is doing is trying to think, okay, how can we represent the actual shape, right? Because it's not, a channel is not just the width and the depth, it's actually, there's a shape to it, and that shape can change a lot. So she's using a combination of several data sets, and one of them is what's called eHydro, which is a sonar surveyed by the Army Corps of Engineers. So the Army Corps of Engineers, they are responsible of keeping our navigational waterways open. And so they go and depending on the, how active the river is, they go with a sonar, with a boat, with a sonar, and actually take mapping of the bathymetry of the river periodically. And finally, someone again decided to compile all of this into one data set. So Riley can go and actually measure the profile and see what the shape looks like, and she's working on a different method of trying to represent those with different approaches. And it looks very promising. She just published it, or not published, she just presented this last week I think it was last week, in her thesis defense, not thesis proposal defense. And I sent her a note the other day, please send me, your presentation so I can show it, because this was the first time I saw these slides, which looks really good. So I was kind of excited to share it with you. I mentioned the bankful discharge, where this is absolutely crucial, and really there's the state of the practice right now of estimating when flood commenced is using what we call reoccurrence interval. So everyone here that's heard about a flood or any extreme event, we always hear 1 in 100 years, 1 in 1,000 years, 1 in whatever, 500 years, and so on. So the same concept is used to estimate in bankful discharge. So you take, in most cases, use 1.5 or 2 years reoccurrence interval as your bankful. This has been shown over and over again to be highly inconsistent in terms that it's really not a good measure of bankful. And so we are developing data sets it's going a bit slow because it's actually hard to find good observations of bankful discharge. But eventually our goal is to use machine learning or maybe even simpler approaches to estimate bankful discharge. And I think if we can prove that it's working well, it can make a really significant and almost immediate impact on operational hydrology at the Natural Water Center. So I'm really looking forward to that happening. I mentioned our desire or our need to develop a repository of flood maps that we can actually then compare the improvement that we make into real observed flood inundation. We've done a pilot of that some years ago, and that was pretty well received. And we wanted to scale it up orders of magnitude. So I don't know if there's anyone in the room that does remote sensing of floods or have flood data. We want to eventually create a repository that will be open to the community so people can contribute to it. And obviously it's going to be open that people can download it. However, we started doing that. I have a postdoc that actually works on that explicitly. But I decided to actually take a step back. I was really excited. Okay, we're going to do this. We have the money. We have the postdoc to work on it. Let's do it. We can do a lot of good. But I decided, wait, you know what? Actually, we don't know, we the community don't know how to use remote sensing of floods in order to properly evaluate models. And is the slide coming? Yeah, it is here. And that's because remote sensing, anyone who's done any remote sensing know that remote sensing is a highly biased enterprise. Or not biased is not a good word, but it's not perfect by any means. And in the context of flood inundation mapping from space or from aerial or even from drone, the problem is it almost doesn't matter which sensor you use. It can be radar, it can be optical. There are limitations of what you can see, especially if you have dense vegetation, buildings, or urban environments, and so on, or cloud cover for optical sensors and so on. So we have, this map on the left, you see this is a flood map that was generated from SAR, from Sentinel-1 imagery, and it's pretty typical. This is not unusual to see because floodplains tend to be very have high degree of vegetation, especially in the southeast, but even elsewhere. And so the satellite can see patches of flood, but can't see the entire domain, and likely because there's vegetation here or some other obstacles. So we ask ourselves, all right, that's good. That's, let's say, the state of the art of remote sensing of flood, but can we actually use this as is to evaluate our models? And my answer was, no, we can't, or we shouldn't, because in some locations, the model may be right in predicting flood, and the remote sensing may be wrong because it just couldn't see it because there's vegetation. The model doesn't necessarily care about vegetation. It can still flood under trees, obviously. And to my surprise, there's been very little work on this problem because modelers, they use whatever data they can get to evaluate their models. So they don't really think too much about the problem in the remote sensing data. And remote sensors, well, they're just trying to predict or produce the best map that they can. It's not so much their concern that you need to use it for evaluating model. So this is something that's really, really new. I've been kind of obsessing about this in the last couple of months. And I came up with a strategy to try to take an imperfect remote sensing flood map and make it not perfect, but something that can be more robustly or used more robustly into predicting our models. So I'll skip the details here because I do want to cover more ground. But in a nutshell, what we do, we came up with I call it the gap fill algorithm or tool that tried to guess based on topography whether or not the gaps within a flood maps are flooded, based again, just basic topography. If it's lower, it's flooded. There's much more to it than that. And then I came up with a strategy of how to use this new, let's call it augmented or improved flood map. And it's not just, okay, I fill the gaps and I'm going to use it to evaluate my model. That's not going to work as well. So in a nutshell, what we do, we remove all of the uncertain pixels out of the evaluation. So pixels that were not observed by the remote sensing as being flooded and were not observed by the gap filling algorithm to be flooded are probably not flooded. So we can call them true negative. And then pixels that were observed by the remote sensing, we can call them true positive. And the one in the middle that were by remote sensing, but not, by the gap filler, but not by the remote sensing, we don't know exactly. So we're just going to remove them from the analysis. And that actually, this is quite a busy slide, but basically using this approach, we found that we can mimic in terms of the model evaluation, what we call the true map. This is a map that we have a lot of confidence in. So this was a very good result, better than I, to be honest, could have hoped for. So I'm just looking forward to the time that I actually have to, if I can get some time to actually write this up into a paper, hopefully in the next 10 years. But it's coming, I'm sure. I was pretty obsessed about this. I got some questions about this. I'm gonna mention this. This was, go back a few years. This is a tool that I was the lead developer of to augment remote sensing. This is unrelated to model evaluation. This is about taking flood map from remote sensing and adding water depth to them. And this came from actually people requested that because my colleagues at the Flood Observatory, they produce flood maps all the time, in real time or near real time. And they asked me, can we estimate the water depth? Because estimating the extent of the flood, that's very useful, but the depth is really directly linked to damage and impact and so on. So obviously there's a big difference between 1 feet of water and 6 feet or 9 feet of water. I think people in Florida understand that very well. So we developed this tool, very simple GISC, I call it, tool that basically took the flood extent polygon and the DEM, and we did quite a bit of the evaluation of it. And as you can see from this last slide, there's been a bunch of papers that came out of it. And this has been really well received. It was very important to me to make it all available. I don't know why this slide wants to go so fast. But anyway, I guess it doesn't. I see someone trying to take a picture here. I'm gonna. I don't know. 5 seconds, 2 seconds, and it's gone. I don't know. I guess I didn't really want this. Subconscious of me didn't want you to see that. No, but seriously, we had everything's available online on GitHub, Google Earth Engine, ArcGIS tools, ArcGIS notebooks, and so on. Another thing, just very quickly, this is another really well-received paper that we published a couple of years ago with a master's student looking at urban flooding. This is something that I'm very interested in, but have not really, beyond this paper, has not really go into. This is something that we, in the context of the National Water Center, really needs to go into. We're not there yet, but we just have to, because that's where people are. So I always tell people that a flood is not a natural disaster, right? It's a natural phenomenon. it's a disaster once people are involved or property and people get hurt or damaged. And so urban is where most people are, so we need to do a better job. This was a pretty cool study to actually simulate flooding at the University of Alabama campus. So all the stormwater infrastructure, and then playing around how important is the stormwater infrastructure, because that's one of the big problems we have, is that we don't have the stormwater infrastructure data for most locations, even in the US. And so we first wanted to see how impactful it is it to have it properly mapped in your model simulations. And at least according to our results, it's very important. Even for very large storms, it still make a big difference whether or not you implement your stormwater infrastructure in your model. All right, so I don't have a lot of time, but I do want to talk about my global riverine modeling. And I like to show this picture that I generated from Google Earth. And I often ask people if they can guess which river are we looking at. And the hint is it's not looking north, so don't think of it as a regular map. So I don't know if there's any guesses in the room of what river is that. It's a large river, Amazon, thank you. So this is the Amazon River, and it's because it's so big, it has so much sediment. I really like to show it because you can really see the sediment, right? You can actually see the sediment from space. It's such a huge, and you can see the sources of sediment. Here we have the Rio Negro, which is a very low sediment bearing river, and you can see that it's very dark. And you can see that most of the sediment come from the Andes, so it's just a lovely picture. And kind of a pitch to Anushka's master paper, which is all these deforestations, all the human elements that's going on in the Amazon. So I'm not going to talk about Amazon specifically, except for one slide, but I'd just like to show it. So what is our motivation in doing global scale modeling of rivers and sediment in particular? Some people question that, and I definitely had people question, why are you doing this, or why is this important? Especially people who look at very small scale rivers. And I think most people don't need to be convinced, or it's not too hard to convince them, that we are facing global problems and global issues, and everything is connected. Climate change, population dynamics, our freshwater systems, I think you all know, are under peril in many parts of the world. So having a uniform global scale modeling framework is important. It's not a substitute for local knowledge and modeling, but I found it, and I hope I'll convince you that it can be useful to gain a large scale picture of our freshwater systems. So this work started when I was a postdoc at the University of Colorado, and we developed, I would say, one of the first spatially and temporally explicit global scale sediment flux models, fluvial flux models. This model is called WBM-SED, and it's, I'm going to talk a little bit about this. It's all open source, and we've used it, and other people have used it in quite a few papers over the years. WBM-SED is based on the WBM plus hydrological framework. So this is your hydrological model that predicts discharge in global rivers. And we develop a sediment component to it, or multiple sediment components to it. I'm gonna go pretty quick here. So the sediment itself, or this, I should say, the suspended sediment itself, is a pretty simple set of equations, empirical or semi-empirical equation that estimate the average sediment flux as a function of discharge, drainage area, relief, air temperature, and B, which is this lithology, trapping efficiency, which I'm going to talk a little bit about, and then some anthropogenic erosivity factor. So very simple, but it works quite well at the global scale for large rivers. We also added some component, although never published this, of nutrient and organic carbon. Now, just to give you a sense, I'm sure, I don't know, most of you, or almost perhaps none of you, have ever ran or dealt with global scale modeling. So in this case, we use a relatively high resolution, especially for the time, which is 6 arc-minute. It's about 11 kilometers in the equation. And the model is fairly efficient. It can run 1 year of simulation in 1 hour. So we can run decades if we have the data and if we have the time. We run it on a supercomputer, but really it can run on a laptop if you have enough time, basically. It's just a really data-heavy model, so it's better to work on a really large machine. You can run it at much higher resolution if you want to. Again, this data-dependent, time-dependent. I was a few years ago, I was on sabbatical at the University of Hawaii, which was, as you can imagine, really hard year for me. But I was really interested in Hawaii suffered from a lot of problem with sedimentation to the coast. It affected their coral, their tourism, water quality, and so on. But surprisingly, there's actually not been a lot of research to do modeling. So I was curious and I was trying to use my own model. So scale my global scale model to very high resolution at the Hawaii scale or Oahu scale. So one island in Hawaii, and it worked fairly well, actually, without much calibration, which was surprising. One of my joys with this work has been that other people have either adopted this model or used the data that the model provides to do different type of research. So this is one of the, I guess, more well-accepted papers that came out of a group of colleagues of mine in the UK, University of Southampton. Francis Dunn at the time was a PhD student with Steve Derby, and they decided to adopt the model and use it to look at the future and see what will be the potential impact or what will be the future of sediment flux into 47 large river deltas in response to climate and anthropogenic change. So river deltas, those of you who are familiar with, are suffering from a lot of issues. Sea level rise, subduction due to groundwater and compaction and so on, but also because of starvation of sediment. River deltas are basically a dynamic equilibrium between how much sediment is coming from the river and how much energy you get from the ocean to remove that sediment. And so if you disrupt that equilibrium by trapping the sediment in dams or disrupting it in any way, or even introducing more sediment, so it doesn't have to be a reduction. So anyway, but Francis decided to look at climate change scenario, climate anthropogenic scenarios, and future dams. So she took a data set of future hydroelectric dams in the world by the year 2050, if I'm not mistaken. That's, or maybe 2099, I don't remember exactly the details. And she calculated the statistics of how much sediment is going to be potentially reduced or added to each delta. And then she did, well, I mean, it's a very complicated paper, so there's a lot there. But she found that most of the deltas will see a decline, and most of this decline will come out of hydroelectric dams. So something to be aware of, if nothing else. There's always a price to everything we do. Not that we should avoid putting more dams necessarily, but just know that there is a downstream consequences, and some of them may be quite dire. Another example of the use of this model, this is my former student, Nishani, who looked at, this is her master thesis, she looked at climate change scenarios. So she took an ensemble of RGC, of general circulation models at different scenarios and said, okay, given all of these models and scenarios, what would be the potential impact of just climate change without any humans involved in the end of the century in all of these global rivers? And again, there's a lot to this paper. This was a paper that Nishani published as a PhD student in 2022, so I guess 2 years almost ago. This is something that I was really, really excited about because sediment trapping is one of the most important anthropogenic effects on freshwater systems, especially sediment. But we, to date, had not had a good way to represent that in our models, I should say, because it is a very dynamic and difficult thing to predict. And the models that we use, or the equations that we use, were not good. We know that they were just not good. So we teamed up with John Gardner's, who is a remote sensor, who developed a data set for sediment concentration in rivers in the US. So now with his data, we actually had observation of sediment concentration for all the large and medium-sized rivers in the country, going back to the 1980s, based on Landsat satellite constellation. With this, we finally had data, right? We know where the dams are. We know, and we can see this is a profile of the Missouri River from its upstream area until its confluence with the Mississippi. And you can see the ups and downs in sediment concentration and flux. These are the two different lines. And these shaded areas are the reservoirs, the big reservoirs that you have. And you can see that once the river enters a reservoir, sediment drops dramatically. And then after the reservoir, it sometimes tend to go up, maybe because of a confluence, or in other cases may go up more gradually or recover. We call it the recovery from the reservoir. So anyway, we have this data. Finally, we have data. So Nishani developed a simple empirical model to actually now predict that more accurately, and we can plug this into our models, and she showed that it works quite well, definitely better than what we had before. And here we come to the Amazon and Anushka's work as a master student, and I asked Anusha a very simple question that ended up being the bane of her existence for 2+ years, which is, we know there's a lot of deforestation in the Amazon. We can see that clearly, as I showed you earlier. There must be a very, very significant signal of that deforestation of sediment flux in the Amazon River. And we can go to John Gardner again and ask him to do his magic and give us the data for the Amazon in terms of sediment from space, from satellites. And yeah, this should be easy. And it wasn't. It was actually, we could not find a very clear signal because it's complicated, and the Amazon is complicated for many reasons, but she ended up writing a really nice paper, which I think is going to be accepted really soon. It seems like it. It's just revised and submitted just recently, and I think it's going to pass. But what we showed there, that there is, if not, there's a lot of text on here, but first of all, that it's actually very complicated. There's no very clear signal where you get more deforestation, you get more sediment. That just did not show itself. We do see a lag. So there's a legacy effect. So it's not that the intensity is necessarily of the amount of deforestation is what predicted. It's a combination of different factors, how long it's been, how densely the deforestation is. We also speculated, although we didn't have data, that it's not all deforestation is the same. It's also what they do after they remove the forest and so on. So it was well accepted by the reviewers, and I think it's going to get published, and I'm happy that we made a stab at that problem. I'm gonna skip this bed load thing because I ran out of time. I know there's another event here in 10 minutes, so I'll stop here, and I'm happy to take any questions. Yeah, thank you.
We do have time for a couple of questions. I'm sorry, a question from the audience.
So as a remote sensor, I'm going to ask you about remote sensing. How did you get the remote sensing data for your Amazon study?
So what John did, he has a machine learning algorithm that he developed in Google Earth Engine. And he takes the entire Landsat repository from Google Earth Engine, and he calibrates it. Originally, he calibrated it for the US from grab samples in many USGS locations. And he published a bunch of papers about it, and he showed that it works well. What we did in this study, actually, Anushka looked at, correct me if I'm wrong, but did compare his remote sensing data to the in situ observations, and they were very strong, right?
Yeah, I don't remember the percentage with the RMSE, but the model metrics were aligned with other established.
So it works pretty well. The sediment concentration works works quite well, surprisingly perhaps, but it does work. At least we use yearly averages, so we didn't try to do, you know, daily or scene to scene, and it's worked. It works.
I'll follow up.
I'll send you the paper.
I really appreciate you talking a lot of really cool stuff and way more math than I can wrap my head around. I'm a 5-year chemist, Riverine, nutrient cycling by training. And I always am jealous of people that study sediment transport because it's more just kind of physically based, whereas like nitrogen cycling, phosphorus cycling, transport has the physics and has the biology of the chemistry and everything. So I'm wondering, I know you had one slide, you said you've done a little bit of work on global like TN, TP transport. Have you tried to delve further into those more kind of complex biogeochemical sensitive solutes or analytes?
We didn't really go very far. I had a project, we got a bit of funding many years ago to try to look at carbon, nitrogen cycling in rivers, but my role was very minor in this. By the way, it's the first time anyone told me there's a lot of math in my math.
Modeling.
My math is so simple. I try to keep it that. No, so to your question, not much. I did work with the folks who developed these particulate carbon and nitrogen and phosphorus equation. They are super simple, basically. They're purely empirical. There's almost no biology, basically, just purely empirical data matching.
Thanks, that was a really good talk. And I want to go to back to the beginning a little bit, where you're making predictions of the flood and inundation extent. Maybe this is peculiar to the extremely flat hydrology here in Florida, but we have these circumstances that's being exacerbated at the coast, but it's where we get floods that are back propagated, so backwater effects that are and I wonder how the model deals with that, or is it just it doesn't deal with that, and so those are flood inundation extents that are poorly captured by the framework?
Yeah, it's a great question. So the more complex model, what's called hydraulic models, they can deal with this. If you give them the data, their equations are sophisticated enough that they can do these backwater effects. The simple terrain approach by themselves cannot, and that was part of their problem. So there was a bit of a trick or a hack, let's call it. I wish Fernando was here because he would have been able to present it, because he was the one who actually developed that. So they do a bit of a trick where they do different scale, do these simulations or estimation at different scales, and it sort of mimic to some degree, or can not mimic, but overcome to a certain degree the backwater effect if it's not too difficult. The problem they had originally was that each small watershed was independent. So if you had a lot of water in the main stem, the small watershed didn't know that, so it would not fill up. The water would not allowed to go. And so by doing different level path, as they call it, they kind of mimic that, but they don't explicitly simulate that. So, and by the way, talking about Florida and hydrology, some years ago, one of my current PhD student and former master student, she worked on the effect of hurricanes on flooding. And she had one of her case study was in Florida, and I said, don't use that. Avoid Florida at all costs. It's not going to give you good results. This is so different than all the other watersheds that you have in the rest of the country. Yeah, we think we're aware of that.
I can make a comment too about the 1.5 year recurrence interval. I think that's largely based on, streams that again are not lowland floodplains at all. So I agree with you on that number it's just unreliable.
So the Water Center had done an analysis a year or two ago where they with the limited data that they did have, they said, okay, what is the actual reoccurrence interval that best match rainfall in different parts of the country? And they found that it just varies a lot. It can be less than a year in some places, and it can be over 5 years in another start. And there is a regionality to it, but it's not so strong that you could say, okay, reoccurrence interval of 5 in Texas and 2 in Michigan. That's not as well.
You go ahead.
Question.
No, you go ahead. It's fine.
Sure.
You already know.
So one other question, I live very close to a floodplain. 1 square foot of my house sits in zone A, and it's been a real pain in my ass. But I wonder whether FEMA has been sort of paying attention, especially your urban simulations, where you're able to sort of capture some of the temporal heterogeneity. And I also note that the stormwater infrastructure is important for predicting flood risk. And is that, I mean, NOAA and FEMA, I don't know whether they talk to each other, but maybe you're the conduit?
FEMA is actually, it's not really explicitly involved, unfortunately, yet. They are aware, let's say it, but I think changing the FEMA insurance program will be painful and slow and difficult, because to be in their defense, it's quite a mammoth effort, and think about how much money was invested over the decades to generate it. They do try to update it, but I mean, I know you're right. It's when you talk to people, especially hydrologists or people that work with flood risk and flood mapping, and you talk about the FEMA flood maps, people always these maps are useless. I don't think that's true that they are useless, but I can definitely see how they are not optimal, let's say.
In the interest of time, we have to end there. Let's thank you, Dr. Zagini Cohen again.
If you didn't sign already, please sign your name on the sheet in the back